Hey everybody, let's talk about calculating the pH during strong acid, strong base titrations. So the key to pH calculations during a titration is to ask yourself what's in the beaker or what's in the flask. That's what's going to determine the pH. We're not going to do any new kinds of calculations in any of this process. It's just a matter of deciding which type of calculation that you're familiar with is appropriate to apply. There are 4 different times we can talk about calculating the pH. We can talk about calculating the pH before any acid or base is added to the flask. And if we just have an acid or a base present, we're going to use our ice table and we're going to calculate how much of the acid or base has dissociated into hydroxide or hydronium ions and calculate the pH from that. We can also calculate the pH before the equivalence point, but after we started adding acid or base to this titration. And before we reach the equivalence point, we've used up some of the acid or some of the base that was already in that beaker, but we have not used it all. And so we have excess acid or excess base. We do still have acid and base present, but in this case, we're going to want to make sure we use a BCA table because since we've added acid or base to it, we've changed the volume and therefore changed the concentration beyond just what the chemical reaction has done. We can also talk about finding the pH at the equivalence point. For a strong acid, strong base titration, we actually form water and a salt that consists of spectator ions. And so for a strong acid, strong base titration, what I have in solution is water, spectator ions, and therefore my pH is going to be 7. And then last we can ask ourselves, what's the pH at some point after the equivalence point? In that case, we've added excess base in the titration of an acid or excess acid in the titration of a base. And so it's that excess acid or excess base added that will determine the pH of the solution. If we take a look at what these things mean for the pH, if we are titrating an acid, so we're adding a base to an acid, then when you start out, you're going to have a pH that is very low because it's going to be acidic. And then as you begin to add base to that, the pH is going to slowly increase, but since there's still excess acid, that pH is going to remain low. And then as you saw in lab, when we come close to having equal amounts of acid and base, we are going to see a sudden jump in the pH as we reach that equivalence point. And then as we continue to add base, the pH is going to rise very rapidly and then it's going to level off as it is the excess base that's determining the pH of the solution. A mirror image curve is seen for a base. Since we're starting with a base in the flask, the pH is going to start high. And then as you start to add acid, that pH is going to slowly decline, but there's still excess base, and so that pH is going to remain high. And then when you reach close to, when you get close to the equivalence point, you're going to see a sudden change in that pH. It's going to suddenly drop. And then as you continue to add excess acid, that pH will stabilize, but it's now acidic, being determined by that excess acid. And that real sharp change is a characteristic of a strong acid, strong base titration, in titrations in general, but you will see a nice, well-defined jump in pH. If we take a closer look at the pH of the equivalence point for a strong acid, strong base titration, we will find that that pH is going to be 7. So the classic strong acid, strong base titration would be hydrochloric acid and sodium hydroxide. And since there is a strong acid and a strong base present, this reaction will go to completion. And it forms water and sodium chloride in this double replacement reaction. Well, water is not going to impact the pH of the solution. pH is going to be right around 7 in a solution of pure water, while sodium chloride consists of spectator ions. So it's not going to impact the pH of the solution. And so you will always find that for a strong acid, strong base titration, the pH is 7 at that equivalence point. If you look at this reaction from a net ionic equation standpoint where you remove those spectator ions, this emphasizes again the fact that what you're making is water, and what you have in solution at the equivalence point, since all the acid and all the base are gone, is just that water, and so you'd expect the pH to be right around 7. So let's take a look at the math for all of these different points along our titration curve. If we have 50 milliliters of 0.3 molar nitric acid and we're titrating that with 0.1 molar sodium hydroxide, we can start by calculating the pH before any base has been added. At this point, we just have a 0.030 molar nitric acid solution. And since nitric acid is a strong acid, it dissociates completely. And that means that once the acid has dissociated, we'll have a concentration of hydronium ion that's 0.030 molar. We can calculate the pH from there. And so that pH is 1.52. If we then come back and calculate the pH after 10 milliliters of base has been added, we need to start by asking ourselves, well, what's the chemical reaction that's going on here? Once again, we have a strong acid and a strong base present, so this reaction is going to go to completion, and I'm going to draw a standard reaction arrow. I'm going to use a BCA table when I go to work this problem now, because since I'm mixing the chemicals as I'm doing the titration, the concentrations are constantly changing because you're constantly basically doing a dilution problem in addition to the chemical reaction itself. So you have to use a BCA table when you're doing a titration. And if I put in the moles of acid and base that would have been added into that flask at this moment in time, I see that the sodium hydroxide is the limiting reactant. We can complete the BCA table on that basis. So at this point in time, our concentration is going to be dependent on the amount of the strong base that remains, because that's going to dissociate completely. So the concentration of hydronium will be the same as the concentration of the nitric acid that remains. And you'll notice that we've had to stop and recalculate concentration because my BCA table is in moles. And so I need to take that moles divided by the new total volume, the new liters of solution in that flask, which is 60 milliliters. And so I can find a concentration for the hydronium ion, and from there I can find the pH. If we continue to add sodium hydroxide, let's find the pH after we've added 15 milliliters. And if we look at the total number of moles of acid and base that have been added to the flask at this moment in time, we'll see that they're the same. This is our equivalence point. And since at this moment in time I have no acid and no base remaining, all I have is water and sodium nitrate, those are both spectator ions, my pH is going to be 7. The pH for the equivalence point of a strong acid, strong base titration will always be 7. And if I were to keep adding base and overshoot that equivalence point, I can again calculate the pH. And at this moment, if you look to see what's still in the flask at this time, we have sodium hydroxide. And so that's going to define our pH of this system. Once again, please notice that we have taken the time to convert from moles of the base that were present to molarity by dividing by the total liters of solutions. That's the volume of the initial acid that was present in the flask and the added sodium hydroxide. And from once I know the concentration of hydroxide, I can calculate the pOH and the pH. And so at this point, we've calculated the pH at all 4 points along a titration for a strong acid with a strong base. Again, the most important thing is asking yourself, what do I have in solution at each of those moments in time?